Yeah, pretty.
Fortunately, we do not have to do all this work, as we will see in example 7.1, using dimensional analysis. All the data for drag on a smooth sphere can be phoned in a single relationship or plotted between two non-dimensional parameters in the form presented. The form of the function f still must be determined experimentally, but the point is that all spheres in all fluids for most velocities will fall on the same curve. Rather than needing to conduct 10 to the fourth power experiments, we could establish the nature of the function as accurately with only about 10 tests. The time saved in performing only 10 rather than accurately 10.4 tests is obvious. Even more important is the greatest experiment convenience. No longer must we find fluids with 10 different values of density and viscosity, nor must we make 10 spheres of different diameters. Instead, only the parameter must be varied. This can be accomplished simply by using one sphere, for example, 1-inch diameters in one fluid, for example, air, and only changing the speed. For example, figure 7.1 shows some classic data for flow over a sphere. The factors 1/2 and 3/4 have been added to the denominator of the parameter on the left to make it take the form of a commonly used non-dimensional group, the drag coefficient CD, that we will discuss in detail in Chapter 9. If we performed the experiments as outlined above, the results would fail on the same curve within experimental error. The data points represent results obtained by various workers for several different fluids and spheres. Note that we end up with a curve that can be used to obtain the drag force on a very wide range of sphere-fluid combinations. For example, it could be used to obtain the drag on a hot air balloon due to a crosswind, or on a red blood cell, assuming it could be modeled as a sphere, as it moves through the aorta, in either case given the fluid 1p and t, the flow speed v, and the sphere diameter d. We could compare a value for p, then read the corresponding value for c to the d power, and finally compute the drag force F. In section 7-3, we introduce the Buckingham pi theorem, a formalized procedure for deducing the dimensionless groups appropriate for a given fluid, mechanics, or other engineering problem. This section and section 7.4 may seem a bit difficult to follow. We suggest you read them once, then study examples 7.1, 7.2, and 7.3 to see how practical and useful the method in fact is before returning to the two sections for a reread. The Buckingham pi theorem is a statement of the relation between a function expressed in terms of dimensional parameters and a related function expressed in terms of non-dimensional parameters. The Buckingham pi theorem allows us to develop the important non-dimensional parameters quickly and easily. In the previous section, we discussed how the drag F on a sphere depends on the sphere diameter d, fluid density P, and viscosity U, and fluid speed V, or with the theory or experiment being needed to determine the nature of function F. More formally, we write where G is an unspecified function different from F. The Buckingham pi theorem states that we can transform a relationship between a parameter of the form into a corresponding relationship independent dimensionless parameters in the form where n is usually the minimum number, or of independent dimensions, for example, mass, length, time, required to define the dimensions of all parameters.
Get that?
So.